First, I'm thankful for this opportunity to talk and participate in this workshop remotely. So, go straight to the subject. I would like to discuss about gravitational wave counterparts at the radio band, so science priorities for Argos. I will discuss for which specific gravitational wave counterparts and what I want to say about them, and I will stick to the radio band, what we have observed so far, and why it is really important to monitor in the radio band these counterparts. So first, which gravitational wave sources I'm talking about? Black hole mergers. As Luca was pointing out, we have observed so many of them, but no counterparts expected or detected so far. The next one is black hole neutron star mergers. We have detected some. We don't have a lot of details for the counterparts. So we expect something, but maybe it's not possible and easy to observe these things. Maybe one reason for this is because the mass ratio is too large, and a black hole of around 20 solar masses will tidally disrupt the neutron star very quickly and maybe accrete it, and only some mass is ejected and all the other goes straight to the black hole. And stick to the neutron star mergers for the rest of my talk. We expect a lot of electromagnetic counterparts, and we have observed a lot of them in this one specific case, which I will be talking also during my talk. Now, the timeline of a merger, a neutron star merger. I will first start with the gravitational waves. The first part, the two neutron stars come closer and closer, and this is the point just before merger that our ground-based gravitational wave detectors can see something. And this is the first part. Then the merger happens, and for some time we are not sure. There are a lot of dependencies on this about the equation of state, the mass ratio, the total mass, how long a hypermassive neutron star will be still there, being alive and doing several things. This is really important. If we can observe this gravitational wave part, this is really important for the equation of state and neutron star physics. At some point, we expect that also, of course, depending on the parameters, will collapse to a black hole, and the black hole maybe emit some gravitational waves like quasi-normal modes, and then continue to be there stable for seconds, days, and a lot of days. All this timeline, of course, will be accompanied with a lot of electromagnetic emission. To begin with, in the phase prior to merger, okay, the two neutron stars come closer, then they merge, the second part here, and you have a hypermassive neutron star from the merger product. Then you expect a jet to be formed when the black hole is formed. Then you expect to observe the kilonova and the afterglow in time. So let me take this step by step, point by point, and discuss more on this. So first, let me begin with the part before merger. In order to model these things at the really late stage before merger, you need to use three-dimensional numerical relativity simulation. What I mean numerical relativity is that you solve also for the space-time, solving Einstein's equations, because this changes as gravitational waves emitted at the two neutron stars come closer and closer. As you can see from this specific simulation, the magnetospheres of the two stars already interact before merger. And this is really important because this can give you a radio signal before merger. However, you need a wide field, you need a blind search to find this. You don't know from where this will be coming. Now, in the second picture on the right, when these two neutron stars merge, there are a lot of different scenarios that will happen. One of these is the prompt collapse, and this is what I'm simulating here. What is the prompt collapse? The two neutron stars are either too massive or the equation of state is too stiff, and they quickly collapse to a black hole without leaving out any accretion disk, or at least minimum density around the black hole. In this case, the whole magnetic field, the whole magnetosphere that was before there alive and giving will dissipate away, and this again will give you another radio signal. Going to more detail to this, okay, this is luminosity, okay. and the time scale is seconds prior to merger. Okay, this is time minus t merge. So 0 is the time of merger. If you go several seconds before merger, it's not difficult to have some models analytically and know how this the luminosity is going up as the two neutron stars approach each other. Then for the last tens of milliseconds, you have to do semi-analytical work. And then for the actual merge, which is here, for this millisecond of merge, I have this in plot where I show the actual merger. So in the actual mergers, you see that the electromagnetic luminosity jumps at least 2 orders of magnitude above what was expected prior to merger. Again, I'm saying that this is the specific prompt collapse scenario, so not something similar with what we observed in the one binary neutron star merger we have observed so far, GW17, etc. And this prompt collapse, it means that after the merger, the whole product collapsed to a black hole really quickly in half a millisecond. You see this peak here, and then this the whole magnetosphere dissipated away, and this gives you a pulse 2 or 3 orders of magnitude from what was happening before. So this needs blind search and wide field, and maybe this is one important model for fast radio bursts. Okay, that comes of course from cataclysmic events, and they're not expected to repeat. So going to the next part. Now the two neutron stars have merged. You have a binary neutron star product. Okay, let me show a video on this. So this is just the last few orbits before they merge. And as they merge, you see that a big core is formed in the center of their orbit, exactly at the center, and then a lot of mass is ejected from this configuration. And this will continue to happen as long as this hypermassive neutron star is alive. You can see the equatorial plane, and behind is the XZ plane and the YZ plane. So at this point, okay, we believe that a really big neutron star is formed in the middle and a big disk is around it. All of this in blue and red is the matter that was just ejected from the system. Okay, this matter is expected to give the kilonova, at least part of the kilonova that we have observed already. And of course, this thing, as long as it is alive, it will continue to give more and more mass to the system, like from neutrino-driven winds or magnetically driven winds. Now going to the next part. Now this core has collapsed to a black hole. Okay, when the two neutron stars were here, had a lot of magnetic field, their own magnetic field is. And then when the core collapses to a black hole, you have a disk around, and a magnetized structure is formed exactly coming from the black hole. So what is important here to note is 2 points. One, these kind of simulations are extremely costly. So you can only run something like this for some tens of milliseconds. However, if you want a short GRB or a GRB or even a relativistic jet to be formed there, you first want to form this structure, then you want your jet to drill through the ejected mass that has polluted the whole place around the black hole, and then this will give a GRB. And another point to make is that when you do this with full GRMHD, so all magnetic fields included everything, the half opening angle of this configuration is more than 10 degrees. And this I will come back to what was done in the analysis of the one binary neutron star merger we have observed. Then we are going to the kilonova. Okay, kilonova was expected. Going first on the left of the slide, as I said before, the hypermassive neutron star is there. We don't know how much time it will spend and be alive. At some point it will collapse with black hole, and the black hole will produce this jet that will be drilling through the merger ejecta. And last part is the afterglow. So this exact jet, now I have taken this, turned it 90 degrees, this jet is drilling through the merger ejecta. It arrives at some point, if it has enough energy, to surpass the merger ejecta and go faster than them. At some point, you expect the broad gamma ray emission when it arrives at its photosphere, and these photons can freely fly away. And then this continue inside the ISM, inside the interstellar medium. And as it piles up matter, this shock produces the afterglow. This is standard afterglow theory. And as more and more mass is piled up, this continues to expand in 10 to the 16. And when the amount of energy from the piled up matter comes close to the energy of the jet itself, then the jet starts to decelerate. And this can be observed. So I have put above this the gravitational wave and above what we expect to see. And what we saw for this specific binary neutron star merger, we saw the in-spiral and the end of the merger. We didn't see any precursor, radio or X-rays. This phase in gravitational waves, we didn't see it. So the first part that the hypermassive neutron star was alive. However, after some point, we see some gamma rays, and then in some time, we see all the radiation expected from the kilonova. And then we continue after 10 days, I think we started seeing X-rays and radio. And this continued till 1,000 days and more from that merger. We continue to have observations, and these are really important for modeling, for constraining models. And these models can really be used to cosmology, and this is where I will go at the end of this talk. So just a few things. I'm sure you've seen such slides and such pictures before. This is how in time the gravitational wave time frequency goes up at some point, and this is merger, this black line. And then after some time, above we see the light came from Fermi GBM, and after some time, almost 2 seconds, we saw a short gamma ray burst. So the delay here was 1.74 seconds, and you have to put all these puzzle pieces together to understand when it collapsed, it produced a hypermassive neutron star. When this collapsed to produce a black hole so that it can produce a relativistic jet, drill through the ejecta and give you the gamma ray bursts. So what we found out from this analysis is that the hypermassive neutron star stayed alive for 1 second. I don't want to stay a long time to this, but with all this information and the kilonova and the gamma ray bursts, you can do a lot of nuclear physics, discuss about our process nucleosynthesis, neutron star physics, etc. Maybe only one example that I have worked on. So I was discussing before why it is important to know when this hypermassive neutron star will collapse. From this diagram, you can see that as the central density on this axis, and on the vertical axis you have the mass. The MTOV is the mass of the non-rotating configuration, is the maximum mass that you can attain, and then the neutron star collapses. And the maximum mass above this one is for the maximally rotating configuration of the neutron star. So when this hypermassive neutron star collapses, has straight implications of about the neutron star physics, about the equation of state, and you can have a constraint on the maximum mass for the neutron star. Of course, this is really important to have more details from the observations for the kilonova. So you have to know how much mass was ejected, because this mass left the system, or the upper limits of the gravitational waves on the left. So all these are important so that you can draw a self-consistent picture about this. And these are important how you can constrain now. This is a plot from this reference from 2018. They had a different limits at the point. With our limits, you see that most of this equation of state here, because our lower limit goes to 2.1 almost, are ruled out. Okay, maybe go straight to the afterglow. Okay, so the afterglow, as we said before, this jet is formed when the black hole is there. However, these simulations are really, really costly. So what we can do, we want to see the jet to be generated, but also to drill through the ejecta, to go to the afterglow. So what we did, we take this data, we understand how is the configuration after the merger, one black hole and an accretion disk around, and what are the details of this accretion disk. And then now we can start a new simulation starting from the black hole. The space-time now is not changing, so a lot less in the numerical cost. and you have two different models. One, you have the accretion disk and you inject by hand a hydrojet. This is done very frequently in the literature. The other one is you put self-consistently the magnetic field inside the accretion disk and you let the physics tell you how this black hole is formed and what is the outcome of this. One important detail of this figure is that the hydro has the opening angle that you prescribed because you give it by hand. The MHD has whatever opening angle the system wants to give, and this is more than 10 to 15 degrees, the opening angle of the jet outside the cone that was from this hydro. Another important thing is that the hydro is just drilling through the ejecta, and this red line that I have here shows how much mass is actually being ejected there. So all this mass on the right part from this red line is bound to the system. However, in the MHD case, you see that the lot of mass here, which is not part of the jet, the relativistic jet itself, which has low mass but a lot of enormous kinetic energy, all this part of the ejecta has a lot of mass that will leave the system with velocity maybe close to 0.1 the speed of light. And this is a self-consistent event when you, of course, include magnetic fields. And this will certainly contribute to the kilonova. So now go to the standard afterglow model. I will not go to details. The standard picture is this. You have a jet, you drill for the long gamma ray burst through a star. For the short gamma ray burst, the consensus in the community is that you drill through the merger ejecta. At some point, the gamma rays are emitted, and this jet continues to pile up matter and continue to give you this afterglow emission. Now, after so many days from this event, I will give you the full light curve. So more than 5 years after this event, you see that the first afterglow came around 10 days in the X-rays and then around 15, 19 days, I think, in the radio. It's really important to monitor the source for so long. Why it is important? Because all this, the curve and the details of the curve, how it goes up, where is the peak, how it goes down, gives you all the details about the structure of your outflow, the structure of the jet. So radio monitoring of this is really important. And as many points here, observational points, you have the best you can do with your models. Now, one paper that we just submitted, when you do hydro simulation, and this is just a single study with hydrodynamics, just to understand the importance of density perturbations. Because if you saw before in the numerical relativity simulation, you don't have homogeneity in the merger ejecta. So at other points, you can have more dense matter, at other places, less dense matter. And what we found out is that if you introduce this to your merger ejecta and you put a jet to drill through this, this is really important for the afterglow observation. And you see that this on axis, these again are the data from GW 170817, this one and only binary neutron-star merger. Okay, and this is the whole afterglow, and you see that the on-axis perturbations give you something different in the beginning, where the homogeneous jet cannot go through all this data. Now, going to the literature, you see that the viewing angle from different teams was 20 degrees, 30 degrees. At some point, it went down to 16 degrees, and these are red. I will come to why these are red. And the jet opening angle, all of these studies are hydro, have either 3 degrees, 6 degrees, 4 different values. What is really important to have was this VLBI detected superluminal motion. So they detected their source, okay, at 75 days. Even if they didn't have good resolution, they can establish what was the position of the flux android. And then again, in 230 days, you can do the same. And you have how far this point went. So like this, you have exactly how your jet is moving at that time while sweeping up matter in front of this, and the whole situation of the afterglow. Another really important observation, again in the radio band, is how compact is the source at 200 days. So at 200 days, this upper left square is the observation. You can see the compactness of the source. Again, this is really important to constrain models, because you can go to your models and say, okay, I have this jet, it has drilled through the ejecta, at 200 days, it is at that position, how this mimics my observations. And a lot of models were out from these observations. So now these red points are exactly these models that took into account these constraints in the radio band, and the result was the viewing angle is 16 degrees, the jet opening angle is 3 degrees. By using our new 3D GRMHD jets with realistic ejecta, okay, we can do the same, let's say, with them, and go after the afterglow first, because you want to have also the afterglow light curve. You want to model this. We have it in the radio band in 3 gigahertz and in 6 gigahertz. Here I'm showing the 6 gigahertz, and you have some points in the X-rays. You have also fitting the VLBI motion, and what we get is 35 degrees for viewing angle. All these constraints are really important to play with your models, put them down, put as much details as possible, so that your models are physically, of course, motivated, and they are as much physical as possible to have this value. Now, if I take back this viewing angle plot from all this in the literature, hydro studies, in the beginning it was 20, 30, with the VLBI went down to 16, our point will go here. Okay. Now, what is this Kian here in my plot? I was saying before that when you have this MHD run, you have a lot of matter being ejected, and this matter will come just behind the jet. So it's not going with a relativistic velocity, but it's going with 0.1 or 0.2 the speed of light. So as the shock of the jet is propagating and is giving you the afterglow and is going down, at some point this merger ejecta will catch up, and maybe will give you more now radiation than the jet itself. And this is what we were speculating. Expected radio signal from the ejecta, and at some point there was a disputed, debated, I'm not sure what is the consensus about this point in the literature, at this point, that there was an X-ray point that was going, the flux was a bit up than this. From the theoretical point of view, it was expected, I think. However, monitoring at these late times in the radio band would be very, very important to understand what is going on. And now, for the last 2 minutes, going to cosmology. Cosmology with gravitational waves. This is exactly the posterior from LIGO Virgo. This is on the vertical axis, the luminosity distance, and here the viewing angle. You can see that there is a degeneracy. That's why when they estimate the Hubble constant from this detection, the errors are really, really large. What you can do, you have to try and find a way to really constrain your viewing angle. Constraining the viewing angle, can give you the exact position of the luminosity distance, or the actual distance you observed, and this can give you a very good constraint for the Hubble constant. So from all these hydro studies that I was saying before, they found that it was 16 degrees. So if you put this with the gravitational wave posteriors, you can estimate the Hubble constant to be the value that I have in the slide, 68.9. However, using our results with physically motivated magnetic field and a self-consistent jet, I was saying before, the viewing angle is closer to 30-35 degrees, and this cuts this results from LIGO Virgo to a totally different place, and the Hubble constant is larger than what is estimated with the hydro studies. So, and I think this goes closer to the value from the supernova studies about the Hubble constant. So to recap, gravitational wave counterparts at the radio band. Precursor, it's really important, however, it's really challenging to observe something like this. Okay, I would say it's really important also for fast radio bursts cataclysmic models, that they are not repeated. Then afterglow light curve, it's always there. We always expect an afterglow, and we need a lot of observations in time so that we can have a very well monitored light curve, and we can constrain our models. Again, centroid motion, source compactness, again, really important for constraining models, because like this, you can constrain the structure of the jet, and you can constrain in a very good precision the viewing angle. And with this, you can do good cosmology, and that was it.
Okay, questions? Any questions online? He's clapping. He's clapping. Ah, okay. Any questions on Zoom? Okay, well, we have a question in the room. Go ahead, John.
So hi, Antonio. So I hope you can see me. So thank you for the very nice review. So I was wondering about the precursor emission that you mentioned.
About what part?
So I was wondering about the precursor FRB-like emission. So in addition to the FRB-like emission, as you mentioned, you may also have some additional emission that comes even before the previous phase. So how would that look like exactly? I mean, do you expect that to be modulated with the orbital, like, would that be a continuous signal modulated at the orbital period, or?
Yes, okay. So first, of course, it will modulate from the orbital period, and this is the details, and inside the paper, I mean, there are details and analytic solutions of how this will go. However, going close to merger, you are not exactly certain about this semi-analytical modeling here, because you expect, as the two magnetospheres are really close together, you will have places that the field polarity changes, currents and magnetic recognition can give you something like flares over there. So this, I would say, this part some seconds before is rather robust. This, I'm not sure about this black part. So this, maybe you can expect more flaring activity at this point, just before merger.
Okay, any other questions?
Can I just follow that up? So do you have any theoretical expectations of the spectrum of that emission?
I haven't done any such calculations. My understanding will be that you would expect something similar that you have from pulsars. So pulsars, you have a current seed, and you have gaps that you expect radiation comes. There you will have similar things. You have current seeds that will radiate high energy, and also in the radio band. More details in the spectrum, I haven't done any.
Oh, thank you.
Okay, still time for another question if anyone has. Nothing in the room. Okay, if not, let's thank Antonius again.